So now let's take a look at question 7. All right, so question 7, part A. If a series is convergent by the integral test, how do you estimate its sum? If a series is convergent by the comparison test, how do you estimate its sum? And if a series is convergent by the alternating series test, how do you estimate its sum? All right, so now let's take a look at the solution, and let's look at part A first, and that is dealing with the integral test. So it's a convergent series by integral test, and we're asked how do you estimate its sum. So part A, we can use the steps and formula from my earlier videos. This is on the integral test and estimate of sums. And first, recap on the integral test. So suppose f is a continuous positive and decreasing function on the interval from 1. This square bracket means includes 1. Up to infinity, and that's where this non-square bracket, regular bracket, means it's not actually gonna hit the infinity because it's infinity. And let an equals f of n. So you could write the terms as a function. Then the series, the summation from n equals 1 to infinity of an is convergent if and only if the improper integral, the integral from 1 to infinity of fx dx is convergent. It's improper because there's infinity signs. So you have to take a limit. And so on. In other words, so if the integral from 1 to infinity of fx dx is convergent, then the series from the summation from n equals 1 to infinity of an is convergent. And likewise, if this integral is divergent, then the series is divergent. Again, this is based on writing an as a function f. All right, so to estimate the sum, we first need to estimate the size of the remainder. So Rn equals to S minus Sn, and this Rn is the remainder. S is the actual sum, the convergent sum of the infinite series, and Sn is the nth partial sum. And when you subtract this, what you're going to get is just this an plus 1, plus an plus 2, plus an plus 3, plus etc. So this is what remains. And we could see that by first noting that the terms an plus 1, an plus 2, an plus 3, etc. are all the terms that remain, since S is the infinite convergent sum of terms, while Sn is just a partial sum up to n terms. So let's just write this down to illustrate this. So if you have S minus Sn, this equals to, well, this is just the full, S is the actual series, or the sum of the series. So we're going to have A1 plus A2, and it keeps going on, dot, 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 and includes AN, and it's going to get AN plus 2, plus dot, dot, dot. It goes to infinity over there. And now we're going to subtract this by the nth partial sum. So this one's going to infinity, but now this AN, this Sn is just going to go up to n only. So A1 plus A2 plus dot, dot, dot gets over to this AN, and that's it, because it's the partial S and partial sum right there. So this full thing is the full sum. This one is the partial sum. So then what's going to happen is everything that remains afterwards is the Rn remainder. So that's the remainder. So once you subtract this, because these all just cancel. So cancel, 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 etc. Cancels, cancels. So that's all that remains. All right, so continuing further. So now, depending on whether we integrate starting from n or n plus 1, we can have an upper and a lower bound for the remainder. And we're going to be integrating this function right here. Because remember, you need to integrate this by the integral test. So integral from 1 to infinity of fx dx. But in our case, we want to find the remainder. So let's just say we calculate a partial sum. And then we get these terms, an plus 1, an plus 2, etc. So we could just take the integral up to, starting from n as opposed to starting from 1. So if we integrate starting from n, we're going to have the integral is going to be, bigger than the remainder. And you can see this visually. So Rn equals an plus 1 plus an plus 2 plus etc. dot, dot, dot. And this can be less than or equal to the integral from n to infinity of fx dx. And you can see that visually here. So if you have this y-x axis like that. So here's the n value. And this up here is the f of n, like that. Notice how this is greater than our this height over here, which is the an plus 1. Yeah, so this height is over here. Yeah, this value right here is the an plus 1 over here. And this rectangle is just the height of this is just, the width is just going to be n plus 1. So this is n plus 1. They're all going to be just 1. Yeah, this is just 1 because it's n plus 1. So subtract those 2. That's just going to be, well, n plus 1 minus n. They cancel, equals 1. So yes, so all these rectangles, all those are an plus 1. Again, if you multiply by 1, the width is going to still be an plus 1. And this integral, though, is all of it below it. So that includes this extra space. So this whole thing is the integral, not just the square, not just the rectangle. So that's this whole thing. And you could see that when you start from n, this is going to be greater than this. So right here. So this is greater than or equal to this part right here, equal to the squares. So these are the remainder. All these are the remainder. And there's always these extra gaps. That is, yeah, so basically that's the upper limit for our remainder. And this is getting close to our estimating the sum. So that's the upper limit. And now we're going to look at the bottom limit. Yeah, so if we take the integral, instead of taking integral from n, we take integral from n plus 1. And that's starting from here. So in this case, we're going to have Rn equals to an plus 1 plus an plus 2 plus dot dot dot. And it's going to be greater than or equal to the integral from n plus 1 to infinity of fx dx. Like that. And you can see we're starting from here as opposed to previous when we started from here. Now we're starting from here, and you can see this visually. Again, all the widths are just 1. So this an plus 1 goes over here, and these are the extra gaps. So this is greater than the fx, greater than this one. So greater than the integral, because the integral is just going to be all of it below here. So you have that extra gap there. So thus the remainder is between two integrals, and here is the remainder estimate for the integral test. So suppose f of k equals to a k, where f is a continuous positive decreasing function for x is greater than or equal to n, and the series, the summation of an is convergent. So if Rn, the remainder, is equal to s minus Sn, then the remainder is going to be between this integral from n to infinity of fx dx, is going to be less than that, and greater than the integral from n plus 1 to infinity of fx dx. Yeah, so that's the remainder. So now we have an upper and lower limit for the remainder. So thus, likewise, the sum can now be estimated as follows. So the sum is going to be the partial sum plus the remainder. And the remainder is going to be, well, less than or equal to this, using this n over here. So using the upper bound for the Rn. And this is, again, Rn upper bound. And then it's going to be greater than or equal to just partial sum plus the lower bound. This is this Rn there. This lower bound right there. From integral from n plus 1 to infinity of fx dx. So there is, we can estimate the sum of the infinite series that was convergent by the integral test. And all we gotta do is just solve Sn at any point. Then we could just take the integrals and see the how close it is to the actual sum. All right, so now let's take a look at part B, and let's scroll up to part B. So part B, if a series is convergent by the comparison test, how do you estimate its sum? So let's take a look at this. So we can estimate the sum using the remainder estimate of the convergent series being compared. And such as in the example from my earlier video, and here's a link to it. And yes, we'll go over this, and it has an example on that. So this is from the comparison test earlier video. So the comparison test, again, recap on it. Suppose that the series summation of an and this series bn are series with positive terms. So summation of bn there. You have basically two cases. If I or part 1, if the series bn is convergent and an terms are all less than or equal to bn for all n, then the summation an is also convergent. If this series bn is divergent and an is greater than or equal to bn for all n, then the series an is also divergent. Alright, so now here is an example from my earlier video, example 5, that I went over and estimated the sum using the comparison test. So use the sum of the first 100 terms to approximate the sum of the series. Right here is the summation of 1 divided by n, n cubed plus 1, and estimate the error involved in this approximation. So we have this one here, and we're going to compare it to this right here. This is just a p series. And this is convergent, because p is greater than 1 there. So this is 1, so basically 1 divided by n cubed plus 1 is less than 1 divided by n cubed, because you have this extra 1 there. You're dividing by a bigger number at all times. And note that 1 divided by n cubed is a convergent p series. Alright, so since the terms right here are smaller than this comparison one, the given series is convergent by the comparison test. And the remainder Tn for the comparison test, for the comparison test series, or not comparison test, so it's going back here, so the remainder Tn for the comparison series, this right here, we had the remainder already, was estimated in example 5 in section 11.3, as again, earlier video. We'll go over that in a bit here. That's this one right here. Yeah, we'll go over this later after I cover this example. And again, that one used the remainder estimate for the integral test that I just went over in part A. So basically used estimate like that. Yeah, so there we found in section 11.3, we found that the remainder is less than this integral from n to infinity of 1 over x to the 3. And again, identical to this right here. Yeah, this remainder is less than this part right there. And yeah, so this integral right there is just equal to 1 divided by 2 n squared. And yeah, this 1 over 2n squared, we could just see that from the, again, earlier video here. So for reference, here's integral from the example referenced above. And this was from the integral test estimate of sums video. So we were asked to approximate the sum of the series, the summation of 1 divided by n cubed by using the sum of the first 10 terms, etc. And I'm just going to look at that integral. So that's what we used right here. And here's that integral right here. So in both parts A and B, we need to know the integral from n to infinity of fx dx with fx equals to 1 over x cubed, which satisfies the conditions of the integral test. We have so integral from n to infinity of 1 over x cubed dx equals 2 limit. As t approaches infinity, just change the variable just for the limit here. So integral of this, remember this is equal to x3 and x to negative 3, so you have to add a power to it. So this becomes x to the negative 2 because you're adding plus 1 to it. And then you put a negative, then divide this by negative 2 like that. Just remember the integral rule and then carry it down. And now you plug in this n and t. And the t is just because you can't put infinity in there, so you're going to take a limit. So you're going to get this right here. And then you're going to evaluate it from n to t. So then when you put in, yeah, it's going to be t right here, subtracted by this, so subtracted by a negative, becomes a positive over here, and then you plug in infinity, this goes to 0. This goes to 1 over infinity, goes to 0, and you end up with 1 over 2n squared. Anyways, just going over that. So that was the integral that was used there. So the remainder is less than this for the comparison. So therefore, the remainder Rn for the given series, this one here, is going to be less than the remainder. Yeah, less than the remainder of the comparison one. So this right here is less than this right here. And that's because the comparison test, this is smaller. So this one is convergent, but all of these terms are smaller. So this is also convergent. So then the remainder is going to be the same, but smaller terms. So every single one is going to be smaller. So there is how we could use the estimate setup there. Yeah, so this means here, so with n equals to 100, if you plug that into Rn, it's going to be, well, or in this one right here, you get this 0.00 with 4 zeros and a 5. So 0.00005. So the remainder at the 100th n, or the remainder of the 100th partial sum is equal to this right here. It is less than that. So using a programmable calculator or computer, we find that the summation from n equals 1 to infinity of 1 divided by n cubed plus 1 is approximately equal to, and here just plug in up to 100. So we're going to go to, this is S 100. This is S, but it's approximately equal to it because the remainder is so small. So this means that this is going to be equal to approximately 0.6864538, with error less than 0.00005. So that's an estimate. So that was the example we went over. Now part C. So part C is asking if a series is convergent by the alternating series test, how do you estimate its sum? Well, if it's converges by the alternating series test, this one is more straightforward than the other ones because we don't need to take integral or etc. or compare it. We could just add terms until we reach a desired accuracy given by the alternating series estimation theorem as stated in my earlier video. Yeah, so we have an alternating series estimation theorem. If S equals to an alternating series, so summation of this negative 1 to the power of n minus 1, Bn is the sum of an alternating series that satisfies this I, where Bn plus 1 is decreasing, so it's less than or equal to Bn, but it's greater than or equal to 0, so it's always positive. And the limit of Bn is approaching 0 as n approaches infinity, then the remainder, or the absolute value of the remainder, is equal to the difference between the sum, which is the absolute value of the sum minus partial sum, and it's going to be less than or equal to Bn plus 1. Yes, in other words, we always know the accuracy, so what remains is always going to be less than or equal to this term, so Bn plus 1. So if we want to go R100, the remainder is going to be, well, less than or equal to B101. So we just take the next term, and that's how we can get more accuracy. So we can visualize this theorem from the earlier figure. So if we have 0 right here, here's the first term, B1, goes all the way to S1, is a partial sum. And if you go backwards, we go back to S2, but this absolute value is less than. So this B2 is less than B1, and you're subtracting it, so you're going to go over here, less than it. So then the difference between from here and here, this difference, this is going to be our S, it's going to be our S minus Sn, because this is this right here, yeah, this part right here, I'll just put a space here. From here to here is our S2, from here to here is our S, the actual sum of the infinite series is this S1 right there. So when you subtract it, you get this remainder here, R, like that. And this value right here, so this remainder S minus Sn is always going to be less than the next term. So now if you have this plus 3 right here, so that this one goes all the way across here, now you have this S3. So this is, from here to here is B3. So then this is going to be less than or equal to B3. So that's our size. And then if we go backwards now, so now you go backwards again. So from here you go to negative B4, so all the way up to here. So if we start all the way up to there now, that means this is going to be our remainder, S minus S4. So that this is R4. And then the difference, now this is going to be, well, less than this B5 is going to, you're going to go across it all the way there. So you're always going to go, this is B5 there. So because the S is going to be in the center over there. And this is going to be B5. B5. Yeah, so it's going to be less than that setup over there. And this is going to be less than or equal to B5. It's fascinating stuff there. So that's how it is. You can just keep adding the terms and you always know the error. The error is always going to be the next term right here, Bn plus 1. So that's how big it is. So you can just keep adding. So notice that S minus S4 is less than B5, and S minus S5 is less than B6. So this is the S minus S5. The absolute value here is less than this right here. Less than this section there. So it's fascinating stuff.